for alpha and beta in order to guarantee that G hat is going to be a pseudo-Riemannian metric on N. If you give a coordinate system, you have these expressions for the covariant and contravariant expressions. And the point here is you don't need a coordinate system to define them. Like in physics, you just give coordinate system, but you have an intrinsic definition of this formula. That's the important part. But once you have coordinate systems, people realize that these metrics satisfy a group structure. These coefficients you can apply to the metric tensor, and if you change the coefficients and apply it again, you have a group structure that acts on the metric. But the funny thing is that the inverse element of the group has the same coefficients of the inverse metric, this formal metric. And that's really nice, because once you have this group acting, the notation should be clear that I'm acting the floor operator and giving you the covariant components. But I also can do this for the contravariant, and this works because the coefficients works fine. And of course the seal operator satisfies group structure acting on the metric, and you can actually show that these two groups are isomorphic. So they are algebraically indistinguishable, and because of that you can take all that information in one group that acts in the sense of group action in the set of Riemannian or pseudo-Riemannian metrics defining our space-time. That's nice, but this is really abstract. We didn't know before which group is that group that is acting on these metrics. So taking again the equation for this formal metric, you can see that if you take a vector that is perpendicular to V, let's say x, and you put G hat of xx, this term here is going to 0, and you are scaling the norm by alpha. But if you take a vector field x that is parallel to V, you have G hat of xx scaled by alpha plus beta. So since V is fixed, you can decompose any vector field along V and the perpendicular component to V. So that's the idea behind defining this new operator here. You are decomposing any vector field perpendicular and parallel to V according to this formula. And now you can describe G hat in terms of this new operator. So you can see G hat is a new metric tensor, but you also can see this formal metric as having the same metric, but now you are changing the tangent space in each point according to this definition. Of course, you can do this for the inverse of the metric, this formal co-metric. And if you change any covector according to this rule, this formal metric is changed in the inverse way of that. This is going to be important for rainbow metrics that we are going to talk about. So that's what I said. Instead of considering new metric, you can consider the same metric, but now you are messing up with the tangent space or the whole tangent space. So if you want to derive a coordinate expression, you have trivial. You take the vector field, the base, and the dual bases, and then you apply to the operator to get the coordinate expressions. And if you take the coordinate expression, there is a fun fact that you can load the index of the operator, and you can see that this formal metrics, they can be seen like square roots. The disformal operators, they are like the square roots of the disformal metric. But to do this, you need the operation that we defined for groups. And as properties of the disformal operators, you can see that the covariant and the contravariant disformal operators, they act like inverses. The set of disformal operators, defined by D, these guys here, they also satisfy the group structure, and that explains perfectly the group action. Because of that, we know that the group that is acting on the set of metrics is actually a group of linear operators. And these operators they have a unique class, because if you take the expression here, you could take minus or plus here, or minus or plus here. Since this is quadratic, all the minus signs, they are cancelled. You get positive every time. But actually, this is the only class of these form operators that satisfies a group structure, and you can define this formal metric using these operators. So they characterize all of your these formal metrics. And as I said, you can see these formal operators as the square root of these formal metrics. About the causal structure, we all know that conformal transformation, they preserve light cones. So if you have just the conformal factor, your light cones are preserved. So any variation in the causal structure should come from the beta parameter. We proved that if beta equals 0, you have conformal, so the light cones are still preserved. But if you have a negative term, your disformal light cones are going to lie inside the background one, and if beta is positive, it's the opposite. You have disformal cones lying outside. So we prepare an example. Oh, wait, we still have this. Like I said, you can see this as a new metric tensor, or you can see this as the old metric tensor, but using different vectors. So you have disformal metric and vectors, or background metric and this deformed vectors. But the point is they are equal, so it doesn't matter if you apply the left side or the right side, because all it should be equal, because this is a tensor equality identity. And for example, if you take if you take the metric to be Minkowski one, and in a point you have, let's say, v equals to 0, 1, 0, 0, x given by this, alpha 2 and beta 3, because this guy is positive, you already know by the proposition that we proved that the background cone is going to be inside the disformal one. But you can check this also doing the calculation of the norm of x in G, which is negative by definition. It's space-like with respect to G, but if you take G hat, it's positive, and therefore it's time-like with respect to G hat. And you can see this in this nice picture. The red is x, this yellow cone is the disformal one, so it's inside time-like, but it's outside the blue one, so it's space-like. But you also can keep the cone, like this equation suggests. You can keep the cone, but change the vector. That's what we are doing here. You keep the cone, this is the original x, but when you change the vector, it's time-like. So it should lie inside the cone. This is not in scale, of course. And let's see some applications of that in physics. They are working in Brazil, these two fellow Brazilian people. They're working in this formal invariance of the Klein-Godel equation related to scalar fields and the Maxwell field equation related to vector fields. And they found in two papers conditions that these equations are invariant under this formal transformation, but for a while nobody questioned about the spinor case. If there is a theory involving spinors in which you can achieve this formal invariance. So Eduardo had the idea to consider a disformal metric, in fact the co-metric, given in terms of the Dirac current. But now, because the Dirac equation is not conformally invariant, so you have a small class of invariance here. For example, if your conformal factor is constant, you can rescale the mass, or if your mass is 0, you can also have, but this is the main theory, I'm going to talk about this. But we know already that this equation, without the alpha here, the original Dirac equation, is not conformally invariant. So you have a small class of invariant solutions. So the question is, suppose that we have the modified Dirac equation, where the metric is given by this formal metric, What are the conditions for the same spinor field satisfy the Dirac equation in the background metric? The idea behind this, well, the theorem is, okay, if you have this formal metric, they're related by this, where V is the normalized Dirac current. So you have a class of solutions that keep this equation, the modified Dirac equation, invariant. So as I said, if you have massless spinor or the coefficient alpha is constant, then you can rescale the mass. You get this formal invariance of the Dirac equation. The sketch of the proof, it's really long, the proof, but we can more or less grasp the idea, is that you need to write this equation here, this one, use tetrads and the relation between the two tetrads of G and G hat. And then once you do this, you can express that equation as this huge equation, but you can see that the first two terms are exactly the Dirac equation in the background metric. So what we need is to cancel everything here to have the Dirac equation in the background metric. If you can write the spinor, the derivative of the spinor in terms of the elements of the Clifford algebra, this is known as Inomata condition. But in our case, since you have a covariant derivative here and the antisymmetric tensor, you're going to get the vorticity term. So we generalize the Inomata condition, including vorticity. So the sufficient condition to keep this equation, actually this equation, invariant is that the spinor field satisfies the generalized Inomata condition, that you can express the derivative of the spinor field in terms of the elements of the algebra and the vorticity. In the end, you get this condition in terms of these functions, S1, S2, S0, sorry. And this condition comes from the conservation of current, where the prime is the derivative, covariant derivative along the axial current, the I, because you have Dirac current and the axial current. So for the massless case, we don't need Inomata condition, so it's fine. It's easy to find examples. You just need these two conditions. You need sigma to be 0, and you need the derivative of the conformal. Actually, this is the square root of the conformal coefficient to be equal minus b, a third of b, and this is the covariant derivative of j in the direction of j. So if you take this spinor field, it's massless. The Dirac current is constant, so this term is 0 if you take the covariant derivative. And we actually show that the same spinor field satisfies Dirac equation in a non-flat metric if you take the background metric to be Minkowski one. So that was really nice. And the conformal factor you can take as any constant. You rescale the parameters here. That was really nice. But for the massive case, we don't have examples. It would be really difficult to find a solution for that. As another application, we apply the formalism using these formal operators to explain something about rainbow gravity. Rainbow gravity was a phenomenological approach to quantum gravity that you have a modified dispersion relation, changing the momentum space. And because of the way you change these, you have a metric that is energy dependent. And Magege-Smolin suggests that you can do this by an operator acting on the tangent, cotangent space, changing the norm of the momentum. But he did not explain which operator is this one. But then you can use what we've seen before, that when you change the momentum space using this formal metrics, the metric itself changes in the inverse way. So this is perfectly described by these formal metrics. You just need to find the tetrad. That is, once you give, where is it? Next slide. Okay, for this formal metric, you need a vector field. So you take the dual and define the energy as the projection. And you're going to take P0 to be, okay, there. P0 is going to be the co-metric applied to the momentum and this vector field, co-vector field that is fixed. And you have everything in perfect analogy. This is going to be the new momentum in terms of the tetrad, the new tetrad, which are now energy dependent. And this is the relation between the rainbow coefficients of the metric and this formal one, this one. And then you can write in this base your metric like this. So, okay, this is nice, but we need to find out examples in the literature about rainbow gravity, and we found 3 actually, including all possible situations for beta. So the first one given by Magege-Smolin, they consider F1 equal F2, therefore, where is it? Beta equals 0. And we know that if beta equals 0, it's a conformal transformation, and because of that, causal structure is preserved. The second example given by Grazielli, she was a former postdoc here. She considered F2 equal 1, F1 equal this function. And using now these formal coefficients, you get this. And if you plot beta, you're going to see that it's negative. And therefore, speed of light should be less than 1 if you calculate this one. But we already know that because of the sign of beta. And the reciprocal example given by Amelino Gamelia, you take F1 equal 1, F2 equal 2. If you calculate the speed of light using the dispersion relation, the modified dispersion relation, you find the speed of light greater than 1. But if you plot this one, you're going to see that this function is positive, therefore beta is positive, and you have the algebraic criteria to find this. So that's what we did about this formal matrix. So we showed that this formal matrix can be described by operators acting on the tangent plane, the cotangent plane in each point. We show that you can more or less know the causal structure. Sorry. Just knowing the sign of beta, that's really nice. We found a sufficient condition to keep Dirac equation invariant under this formal transformation, and we also explained in the covariant way what people are doing in rainbow gravity, and also it's compatible with the causal structure that they did before. So for the second part, it was about self-force effects on a particle orbiting Weissenostrom black hole. So as you know, this is the Weissenostrom matrix, the only spherically symmetric solution for Einstein-Maxwell equations. Okay. So the main task here is to calculate the regularized self-force. We're going to pass through that of a point-like particle with really small mass compared to the black hole mass, orbiting around the black hole. But this orbit is going to be a circular geodesic. And by scalar charge, I mean a charge that acts as a source for the scalar field. And you can see this work as a complementary of Professor Ruffini and Zerilli. Nice time. And you can see, if you do some Lagrangian mechanics, you can see that the scalar fields should satisfy this equation with a source term, like a D'Alembert equation with a source term, with a source given by this equation. And these are parameters that you need to find out in order to keep your circular orbit a geodesic. Okay, so how can we solve this problem? We can decompose the scalar field in spherical harmonics, and once you plug this decomposition inside this equation, you're going to cancel the angular and the temporal parts, and you get just a radial equation given by this one, where the source term is given by this term. The point is that this equation here, if you take the homogeneous differential equation, the solutions are given in terms of Hoying functions. They are not. really fun to work with, but okay, so we need to use green method, but I'm going to get back to this equation. We solve using green method perturbatively. So in the end, we need to write the homogeneous equation like this, perturbation, and then you solve for any post-Newtonian order you want. But the problem is, if you do this, for some values of L, you have divergent terms. So to include the non-singular parts, we need to use the Japanese technique given by Manu, Suzuki, and I don't remember the other name, Takasuji. So the idea is to express the solutions of this radial equation given in terms of point functions as an infinite series of hypergeometric functions, infinite sum of hypergeometric functions satisfying a recurrence relation, and you need to find the coefficients of this sum. I'm not going to talk about this, but in the end, when you do this, you get your C, but then you need to remove this singular term given by the Taylor expansion of this function. And we are going to use Y and U. U is the ratio between the mass and the radius, the distance from the central object, and Y is given by this. So we found out using Manu, Suzuki, and Takasuji technique, up to L equal 4 and 7.5 p.m. order, this expression, this huge expression for the scalar field. But this is for Heiss and Ostrom. You can see the result for Schwarzschild. When you put W equals 0, W is charge over M, all of that square. And now we can compare, because in the literature people did this numerically. So now we can compare. We found out this. This is our analytical solution using the Japanese technique, and the points are numerical solution. We have an agreement up to 10 to the minus 14 here and 10 to the minus 4 here in the weak field and strong field. That was really nice. To calculate the scalar self-force, we need to take the derivative of the scalar field. So you can do this without regularize. And the only non-zero components are T, phi, and R. You can calculate like that. But then you need to do the regularization of the scalar force, which is the derivative of the other term that we already calculate. The others are going to be 0. And in the end, you get this for Heiss and Ostrom. But again, this is too much. We can do the Schwarzschild case. Again, setting W equals 0. And again, they have done this for numerical procedures. And then we found out that it's perfectly fit, almost that. In the weak field, also 10 to the minus 14, and strong field 10 to the minus 4. The error between the numerical and analytical solution. And also using formulas available, that part is really technical, but using the formulas, we can evaluate the amount of energy flowing into the hole, and in spatial infinity, you find the spatial flow is given by this equation, and this one is the amount of energy flowing into the outer horizon of Heiss and Ostrom. And we define this quantity here, multiplying both solutions by 1/3 of Y to the 4th. So in the Schwarzschild case, we have this simple expression, and in the extreme Heiss and Ostrom case, we have even simpler expression that starts 3 post-Newtonian order beyond the non-extreme case, if you can check the numbers. I need to say that we also did the self-force and the scalar field for Schwarzschild and the extreme case, but we don't have graphics for that, just for the Schwarzschild. What else? Yeah, this is a table relating the flow of energy. This is the relative error. You can see that in the strong field is 10 to the minus 1, around 10 to the minus 1. and in the weak field limit, the agreement is 10 to the minus 4, let's say. So it's in good agreement with numerical solutions. And okay, I'm just in time. Concluding remarks, we have analyzed the cell force effects on the scalar charge of around a geodesic of rising Nordstrom black hole. We calculate up to 7.5 post-Newtonian order, and the scalar radiation flow in the black hole and outside to spatial infinity were also evaluated. The limiting cases of rising Nordstrom, extremely charged, and Schwarzschild were analyzed, and for the case of Schwarzschild, we could compare with numerical results, which are in really nice agreement. And that's it.